do a couple things that are maybe a little different than normal today. I wanted to return to Cole's question from last time, which is what's the biggest number you can load as an immediate? And so we're going to go through and talk about that, but I need to download these two gigantic files first. And then also, I need to download all right, so you guys know me, I'm not in the habit of using PowerPoint, but it seemed apropos for a few things. So let's get back to Cole's question, okay, which is if we do an instruction that's move, register something, and then a specific number, what limits are there on that specific number? Okay, and right, so that's the question. And the answer depends on what kind of architecture you're on. So let's start actually with Intel architecture, and this is one of the advantages of the Intel CISC architecture. So first off, the registers are called different things on Intel. You have, and this is for legacy reasons, back in the old days, there were basically four that you used for like mathematical operations and passing parameters and things like that. And they were A, B, C, and D. Okay, well, as they've extended the architecture over the years, the other thing that happened is that the registers got wider. So at first they were 16 bits and you could address the low half or the high half, and then they became 32 bits, and then they became 64 bits. So RAX, I guess it's time for class. PTSD right there. Yeah. Register RAX is register A extended, right, which means the 64-bit version. And right, okay, so that's not really important for right this moment, but just it's a 64-bit register, and on Intel they're called something slightly different. Okay, whatever. And let's say that we wanted to load in a 64-bit integer, okay, and I just picked arbitrarily here dead beef 1, 2, 3, 4, 5, 6, 7, right? So dead beef, of course, is a valid hexadecimal number, right? Yeah, yeah. Then you saute it with a little olive oil and butter and salt and pepper. No, olive oil is not hex. Sorry. Okay. Anyway, so that's just a 64-bit integer, whatever. And on Intel, you can just load a 64-bit immediate. Bam. Okay. The instruction and the syntax is a little different than it is on ARM. Okay. First off, the instruction is called move ABSQ. I don't want to go into the details of all the different Intel instructions. The other thing is that the order is different, so the destination goes second, whereas normally we put the destination first in ARM. Okay, so I'm going to load this thing into the register RAX, and the dollar sign and the percent sign is just that's what the Intel assemblers expect. So that's just the syntax for them. Okay. So don't worry about that too much. But um, so if we look at how this thing actually gets encoded, and we'll go into a terminal or something here in a minute, then basically every instruction that loads in sort of has a couple of different parts. It has what's called an opcode, and then it also has uh, operands, singular or plural, okay? And so, for example, if you wanted to say add 2 registers and put the answer in this 3rd register, there would really be 4 things: the opcode, and then the 3 things that say which registers are the sources and which register is the destination. Okay. Um, okay. And in ARM, no matter what instruction you're doing, they all take exactly 32 bits to do that. Okay. In Intel, that's not the case. The instruction links are variable. Okay. Now, what this means is that as you're loading in an instruction, loading in data, you don't know that you've hit the end of the instruction unless you say, oh, I loaded in 48B8. That must mean that I'm loading in an immediate and that it's 64 bits. So I should keep loading 64 bits more worth of stuff before I'm finished loading in that instruction. Like, so you sort of have to decode the instruction as you're going. With ARM, you don't have to do that. You just load in 32 bits and then deal with it. Okay. All right. So in this case, um, on Intel, the opcode part also is variable width. Okay. So the opcode could be really short, or it could be a little bit bigger. Okay. And in this case, the opcode is I think it's actually technically B848 because there's an order issue. We'll talk about that later. And then the operand that goes in is the number that we're loading, although you'll notice that the order's a little weird. Okay, so it would actually be 67452301 EFBEADDE. Okay, and the reason for that is think about it's sort of like think about when we were looking at GDB and we were looking at where stuff was laid out in memory. The display seemed a little backwards from maybe what you would have expected. And in this case, right, what it's going to do is it's going to load these things in the order that they appear. So this, uh, it loads them in most significant chunk and then decreasing to least significant chunk, and that gets us this 32 bits worth of stuff. And then the other part, we're loading in most significant to least significant. So, okay, so the order is a bit of an issue. But once you're sort of used to the order problem, then it's not really a big deal. Okay. Okay, so is that okay? Yeah? And so the answer in Intel is you can load whatever 64-bit immediate you want. Go for it. Okay. The answer on ARM is different. And that's obviously what I wanted to talk about more detail. Okay, so 60, or sorry, any questions on that? The number was dead beef 01234567, but notice how the operand is that, but in reversed order, right? The 6-7 goes first. And the 6-7, notice, is the least significant bits of the number. Yeah. Yeah. Okay. Anyway, you mean 8 bits? Or no, wait. Can I not count? no, 2 hex numbers is 8 bits, but there's 4 hex numbers, so it should be 16 bits. So yeah, so my bad. This is an 80-bit thing. Let me. This should be 80 bits right here because we have a 16-bit opcode. So the opcode is 48B8, right? Each hex character is 4 bits, and there's 4 characters, so that's 16 bits. Yeah. Okay.
So why does it, if it's just telling you that you need to like count 64 bits after, then why is it 16? Why can't it just be like 1 hex digit?
Oh, well, because there's lots and lots of other instructions, right? So, yeah, exactly. Now, the minimum opcode width to my memory is 8 bits. Okay, so there are a couple of 8-bit instructions that don't take any operands, um, but those are like, things that have been in the instruction set architecture since the 70s, right? So yeah. Now the other thing here is that I should also mention, right? We're loading in a 64-bit immediate. The instruction for a 32-bit immediate looks a little different. Okay, and that'll actually be the case in ARM also. We'll see that in a second. So okay, all right. Well, let's go on to the ARM issue. All right. So let's say that I wanted to load -1 into a register. Okay, now what we've already done, right, last time, we could load either X0 or W0 with a small number like 3 and everything was just fine. Okay, no big deal. Now, let's talk about the listing of this. And so let me go over here into a terminal for a second. Okay, and well, actually, and also go into Genie. Actually, well, actually, let's take this as the example since we have it right here. Okay, so let's look at that instruction: move W0, comma 0. Okay, so we're loading the immediate value of 0. That's not particularly an interesting number, but there's the instruction encoding for it. Okay, now in a second, let's do 03 and we'll look at moving that number instead. Okay, and see what changes about the encoding. Okay, so let me just do let me just do this. Okay, I'm just literally going to put nothing but that instruction. Oops. Okay, so this isn't a full program, right? So I'm not actually going to be able to run it, but that's okay. I don't care about running it. All I care about is let's look at the listing file that goes with it. We get this, okay? Okay, so what do we got there for the instruction encoding? 6000 8052. Okay, now one of the things that you may find a little bit irritating there is where's the number 3? Do you see it there? It's there, but you just don't see it, okay? It's actually wrapped up in the 6. Okay, and that kind of makes sense because if you take 3 in binary and you shift everything one position, then it might look a little different. Okay, so let's look at that instruction here and see what's going on, and figure out what's the opcode, what's the operand, etc. All right, to do that, we need to open the absolutely massive PDF file. Okay, the one that's like several thousand pages. Okay, the other document that we need to look at is this spreadsheet, okay, which I forget where I found this, but I found it somewhere. This spreadsheet basically has all the opcodes and stuff for and instruction encoding for the ARM architecture. Okay. Okay, so it's gigantic, right? And what was the, let's go back to here. What was it we were looking for? 8052 and 6000. Okay, so what we need to do is we need to go into here, okay, and we can see in this column that what the binary stuff is for all of the instructions, and we know that we're using a move instruction, right? So if I scroll through all this stuff, all the different loads and whatevers, then I can find, oops, I went too far, the move instructions. Okay, so that's this stuff here. Okay, and here's the instruction that we actually used. Okay, so I've lied a bit to you. The instruction MOV is not actually an instruction. It's a placeholder for, depending on the circumstance, one of a few other varieties of instructions. Okay, and in this case, okay, so the move instructions that actually exist, there's 3 of them. We'll talk about what each of the 3 does. There's move in, move Z, and move K. Okay, but there isn't actually move. So if you type move in your source, the assembler is going to pick the actual instruction that best suits the situation that you're going to use. Okay, which might actually not be move in, move Z, or move K, depending on what exactly you're trying to do. Okay, so you'll notice that there's 6 things there listed, but really there's only 3 things duplicated. Okay, and what's the difference? Well, 3 of them are for W's and 3 of them are for X's. Okay, fine, that's not a huge deal. And in fact, if you notice, look at the this column, the SF column, okay, and this is true about pretty much all of the instructions, that very first, or well, very highest bit in terms of significance is a 0 if it's a 32-bit variety, and a 1 if it's a 64-bit variety. Okay, so that far left-hand 1 tells you immediately whether or not you're looking at a 64-bit version or a 32-bit version of an instruction. Okay, then we've got the encoding. Okay, so there's all of this jazz. Okay, and the we have to look at all the rest of this stuff. Okay, notice that the this stuff is basically the opcode. Okay, which tells us which kind of operation we're doing, and the processor needs to know that in order to correctly decode it. Okay, and you'll notice that there's sort of, well, there's three versions. Okay, the stuff in red is the same for all of them, and the stuff in the column OPC is different for all of them. Right, you've got three different versions for the 32-bit guys, and the same things repeated for the 64-bit guys. Okay, so is that all right? All right, we've got this HW field. We'll talk about what that means in a minute. We've got 16 bits for an immediate. Okay, and then at the end, we have 5 bits for the register number. Okay, now let's think about why that makes sense. How many registers do we have on this thing, on our processor? How many general purpose integer registers are there? More than that? 32. Okay. Now, a few of them have specialized purposes, like X30 is the link register and so on. Okay. But basically, we've got 0 up through 31. Okay. So 32 things. How many bits does it take to encode numbers between 0 and 31? 2, 4, 8, 16, 32, right? 5 bits. Well, how many bits do we have here for the register field? 5 bits, okay? Because there are 32 of these registers, and therefore we need 5 bits to identify which one we're talking about. Okay? All right, so all of that stuff gets packed into our 32-bit length instruction, right? 16 bits for an immediate value. The register that's going to be where the data is going takes another 5 bits. And then all this opcode business at the front is going to take another, well, whatever's left over. I can't count this morning. Okay. Is that okay? Right? All right. So at first glance here, what is the answer to Cole's question? What's the biggest number that you can load using one of those instructions? Well, what would you guess just looking at what we have so far?
The largest 16-bit.
Yeah, the largest 16-bit number. Okay, so if I put all ones in that immediate 16 field, right, that would correspond to, as an unsigned integer, 65,536, or 35 actually, because you start counting with 0. Hmm? Yes, the only difference is which register you're putting it into, a 32-bit half or the 64-bit whole. Okay, and because they're all 6 of these instructions are 16-bit immediates, not anything more, right? And now think about it, we can't have a 32-bit immediate. The whole instruction has to be 32 bits, so there's just not room for all 32 bits, okay? You can't. You can only load in 16 bits at a time. Okay, because if you wanted to load an immediate with 64 bits, the instruction width would be more than 64 bits. But on this architecture, what's the instruction width? Every single time, 32 bits, right? So like you just can't do it. I mean, this is kind of like, I don't know, you got 7 hungry frat guys who want to go to B-dubs, and there's only one car, and oh, by the way, it's that stupid little Fiat 500 that sits parked in front of the mall the whole time, right? I want to like take a baseball bat to that thing. Yeah. It is a neat car. When it's what's annoying is not the car, but where it's parked. Okay. So yeah, just saying. Okay. So so at first glance, the answer to Cole's question would be 65535, the largest 16-bit number. Okay, but guess what? Not going to be quite that easy, because what's the one set of bits that we haven't yet figured out what they do out of this particular encoding? Now, the first three are okay, right? These HW bits, what on earth do they do? Homework, yes. Okay. Right. So we got to figure out what they do. All right. So to explain that, let's actually go over to the 40,000 page. Well, maybe not. Yeah. Maybe I should have gotten the 8 gig version of this. Okay. So let me blow this up a little bit. Okay, so this is the operation that we're looking at, right? We saw that it was a move Z operation, okay? And this was the encoding. So in our case, the SF bit, that far, far left bit, is a 0, because what kind of register are we loading our thing into? We're loading it into the 32-bit half, so a W register, okay? If we wanted to load into an X, that would be a 1, and that would be the only difference.
If your architecture doesn't have the capabilities of 64, is that kind of pointless?
Yes, but fortunately we do, right? So, well, like if you, so if we looked at the 32-bit ARM architecture, there obviously wouldn't be a bit that says it's 32 or 64, right? But the encodings would all look different. Okay, this is one of the downsides to a RISC architecture like ARM, is that if you increase the number of bits, you have to kind of redo everything to some extent. Whereas with Intel, you can just tack on new instructions. But then you get Franken instruction set, which is what Intel has become over, the last 50 years, basically. Anyway, okay, so the 32-bit or 64-bit versions, okay, whatever, we've got this 16-bit immediate field, but we also have this HW field. And what the HW field does is it shifts the 16-bit immediate that you pick, okay, by some number of bits, or bytes, I guess, right? So let me just kind of draw this out on the board. This isn't really going to be. All right, so let me think of the W register as having two 16-bit chunks within it, okay? The low 16 and the high 16. Okay, so let's say that I wanted to load in, let's say I wanted to do something like this. Move Z, and then I'm going to load in to which register? Well, let's just say W0. It doesn't really matter for right now. And the number I'm going to load in is the 16-bit immediate FFFF. Okay? If I did that, where would everything end up? What's going to end up here? FFFF. And what's going to end up in any spot that I haven't specified? Well, that's what the Z stands for. What do you think? Zeros. Okay? All right, now, if I did move Z, W0, same thing, but I do, I encode, well, let's see. I encode, let's see, which one do I want? This, okay. If I shift this thing by 16 bits and load it in, where does the FFFF go? Okay, so if I take FFFF and shift it 16 bits to the left, then it would end up here. And what would end up in the remaining positions? All zeros, okay, because it's move Z for 0. So unspecified bits are zeroed out. Okay, is that okay? Now, this is what's a little bit irritating. Can I encode the number 16? How many bits do I have for my HW field here? I only have 2. Can that encode 16? No. Okay. And so what happens here is that the thing in the HW field is the division of 16, or sorry, division by 16. Okay. So what I would actually encode in the instruction here for HW would be 0, 1. Okay. And that corresponds to one 16-bit shift. So I'm not going to encode the actual number of bits I shift, but how many 16-bit shifts I make. Okay, so, damn it, because the thing's too big. Okay, I need to like crop out different sections of that thing so that we don't keep having this problem. But yeah, this is what happens when it's that many pages. Okay. So, so the instruction that would get encoded is if the HW field is 0, 0, I don't shift. Okay. If it's 0, 1, I shift by 16. If it's 1, 0, I would shift by how much? And if it's 1, 1, I would shift by 48. Okay, now, I put a line there because if we're loading into a W register, can you shift? Does it make sense to shift by 32 or 48? No, because you only have 32 bits to begin with, okay? So the bottom two are only valid if you're loading into an X register instead of a W, okay? And the way they would work is the same thing. So the little boxes I drew, right, are the boxes for the W registers. How many boxes would there be for an X? Yeah, there'd be 4 16-bit chunks, okay? And that's why there are 4 shifting versions. Don't shift, shift 1 box, 2 box, or 3 boxes. Okay, so this complicates the answer to Cole's question because with the 32-bit version, this is the biggest number that we can load in with MoveZ, okay, which would be 65,535 squared, I guess, right? Because we've shifted it by 16 bits, right? Well, okay, because then what is this going to be? 1's place, 16's place, 256's place, times 16 again, right? Right. So then this would be the 65,536, but since we've gone 16 bits over, it's going to be times 16 to the 0, 1, 2, 3, 16 to the 4th, which is 65,536. Okay, so it's going to be a big number. Okay, much bigger than we thought, right? And if we go into the 64-bit version, then we actually could get the FFFF all the way over to the far left, right, which would be rather large. And in fact, that reminds me of kind of a handy program that I think I'd forgotten to show you guys. Where is it? I think it's this one. Nope, it's not this one. Okay, there is a handy programmer's calculator. Let me see if I can find it real quick. I think it's called like GNU Calc. No, okay, whatever. I'll find it and but it's basically like a just normal little calculator app, but there's a programmer mode where you can just put in bits and it'll decode them for you, and it's just really handy for that stuff. Okay. Um, anyway, so with move Z, looks like we can actually do much bigger than we thought. Okay. Um, all right, so let me go back to the spreadsheet thing here for a second. Okay, so which instruction was it that we were on? We were on this one, okay, which is going to get encoded. Let me blow this up a little bit so that we can see it better, if it'll cooperate. Okay, so if we were loading in the number 3, which was our example, what are we going to have? We'll have 0, 1, 0, 1, 0, 0, 1, 0, 1. Okay, so that's and I'm going to put some bars in here. 32-bit version, leading 0, opcode. Okay, if we're loading in the number 3, do we need to do any logical shifting? No. Okay, so our shift field will be 0, 0. What's our 16-bit immediate? How do we encode the number 3 as a 16-bit number? A bunch of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, but I want 3, so what is it going to be? A 1 and a 1. Okay, which register are we going into? For sake of example, 0, okay, and so our register field is all zeros. Okay, so I've got this giant 32-bit number. Can we please encode that into hexadecimal? Okay, how do we do it encode it into hex? Take it in 4-bit chunks starting from the right. Okay, all right, so what's this one? What's this one? 8, 6. Okay, what's this one? And this one, and this one, and this one is 8 between the dashes. 8, and then 1, 2, 3, 4 would be 2 and 5. Okay, 52800060. Well, does that look like what we thought it was going to be? Well, huh? Well, okay, so where were we with this here? Okay. Yeah, order memory addresses. Okay. So looking at the thing in our listing file, what, yeah, this is sort of an order issue. Uh, yes, Cole.
Well, isn't it just going like 3, like 6, 0, and it's like going over a 3
Yes, it takes it 2 nibbles at a time. Okay. So 60 is a byte, right? So think of each pair of hex digits as a single byte. What's the um, uh, so 60008052 is that same thing, but kind of looks like it's in reverse order. Okay. And the reason that it's in that order is because um, if I'm loading in this number, right, and I'm loading in 8 bits at a time, the 60 is the least significant bits. Those actually go first, right? Okay, so I think I've mentioned this before. What is this issue called where we have to worry about which end we start at? Indianness, right? So, right, Endian, Indian, okay? Now, have we talked about Gulliver's Travels? Did I bring this up? Surely I did, right? Okay, so what, this is a joke, right? Because uh, of, computer scientists back in the day were well-read creatures. How many of you guys have read Gulliver's Travels besides Drake? You did in 6th grade? It's kind of early for that level of humor. Yeah, yeah.
Too many things.
No, like 9th grade, sure. You're ready for that kind of humor then. It'd be kind of like reading, has anybody read Candide by Moliere? Oh, isn't that hilarious? Yeah. Yeah, this is kind of highbrow humor for 8 in the morning, but you guys will give me a pass, right? Okay. So the joke from Gulliver's Travels, right, is that there's this civilization that basically is split up into 2 factions, and the factions are basically warring over which end do you crack your egg on, the big end or the little end. Well, then that means you're a big Indian. Okay. Okay, but for our purposes, what this means is which end do you load in first? The most significant bits or the least significant bits? Okay. If you load in the least significant bits, then you're little Indian. If you load in the most significant bits first, you're big Indian. Um, and ARM, well, okay, ARM is actually to some extent, it's Indian agnostic. It can be either little or big Indian. Like you can do it either way, okay? But at least with the flavor of Linux we're using and stuff, it's basically little Indian. So that's why things look backwards than they ought to be. Yeah.
Doesn't it need to know the most significant things first, though?
Well, okay, but it's loading in 60 or 32 bits at a time, so it gets it all in one swoop, one fell swoop. And then it just needs to decode it. Yeah. Okay, so does the encoding match what we were expecting? Yes. Okay. Other than yes, the order is a little bit annoying. Just deal with it. You'll get over that. Okay. All right. So we good with that? Yeah. So this is the move Z. Yeah. This? Okay. Well, so if I'm going to parse it, well, let me actually start here. 60 is first. That's on the far right. It's the least significant. Followed by 00, followed by 80, followed by 52, right? So 60 is the least significant, and that means it's listed first there. Little Indian. least significant stuff first. Okay. Now, big Indian makes more sense because then you don't have to reverse the order, but there's other situations where it drives you crazy. So no matter what, you're going to make the wrong decision. Okay. Or maybe better put, damned if you do, damned if you don't. Okay, so yeah, and now we all see why there's no 3 immediately apparent. It's actually sort of wrapped up in the 6 because things were sort of one bit off. Okay, good. All right, so let me go back to the spreadsheet. Hold on, let me find the right spot. Okay, so let's go back to our dead beef number. Okay, now I can only load in dead, right? Because that's only 60, or that's 16 bits worth of stuff. Okay, so if I use this move Z instruction in the 64-bit flavor, then I can load in the dead in one of 4 possible little buckets, depending on what my shift amount is. Okay, and there they are, right? No shifting is down there at the bottom, right? Dead in the far right-hand 16 bits. And then I can shift them in either 16, 32, or 48 bits to get the dead into any of the other positions that I so choose. Okay, does that make sense? So, well, okay. This is not the instruction encoding. This is the actual number that ends up in the register. Okay, and so I guess this is what's annoying. So in arithmetic, in normal math class, how do we write numbers? Big Indian or little Indian? Big Indian. What comes on the far left? Always the most significant bit. Okay, so when I write numbers, I'm going to write them in sort of standard order, which happens to be Big Indian. Okay, so yeah, so that's move Z. Okay, now the Z stands for 0, which is if I don't specify a bit, right, I only get to specify 16 out of the either 32 or 64. What are all the ones that I haven't specified? They're zeros, hence why it's called move Z. Okay, is that all right? No, the 32 versus 64 bit. And that instruction we were loading into W, not X, so that's how you tell the difference. Okay. If that bit had been a 1, then our instruction would have been, well, we would have had 8 plus 5 is 13, so that would have been C, right? So it would have been C2800060. Yeah. Yes? We? No? Bueller? Bueller? Farden? Upside down Farden? Yeah, that's scary. Yeah, people should just carry you around upside down for Halloween, right? Yeah. Okay, so what's then move K and move Z, or sorry, move N? Those work a little bit differently. Let's start with move K. The K stands for keep. Okay, so it works like move Z, except if there's already something in the destination register, it preserves all of the bits with the exception of the 16 that you're loading in. Okay, so what that means is, let's suppose that we first loaded in dead, and then we loaded in beef. Well, if I loaded in the dead part, what would I have gotten? I would have gotten all zeros and then DEAD. And then if I load in beef with a shift of 4, and actually that should be 16, not 4. Then the beef parts get shifted in how much? 16 bits, which moves it one bucket over, but we preserve what was already there, which was the dead stuff. So the result of those two operations would be a bunch of zeros and then beef dead. Okay.
So to get to the to get to that biggest number, it's like four things, all with FF, and then all four of the HW codes.
Yeah.
So is that 4 different commands?
Yes, it's 4 different instructions. Okay. So Cole's point is, if I wanted to load in the very biggest 64-bit number that you can, it's all Fs, right? All ones in binary, right? Well, I can load in these 4 with FFFF, and then add in those 4 with 1 shift, 2 shifts, and 3 shift, and that would take 4 operations with move K. But wait, there's more. Okay. Yes. Order within the next 30 minutes, and we'll include a free ShamWow. Just pay separate processing and handling. Oh, goodness. There were all of these ridiculous ones. Of course, I don't remember hardly any of them, but a lot of them had the word system in it. Like it's the something something system. Yeah. Yeah. Get off my lawn. The wheel. Introducing the wheel. Order within the next 30 minutes and we'll quadruple your order. You'll be able to build a new car. Yeah. The wheel? A little older than that. Probably way older than that. Yeah, no idea. Huh? I don't know. The wheel's pretty useful in agriculture. Yeah. Well, okay. It depends on what you define as wheel, right? Because if you've got a bunch of logs and you put a stone block on top of them and you roll them along the logs are technically wheels. So what do you define as a wheel? No. Oh, okay. Yeah. Okay, so let's yeah. So if we to Cole's point, if we wanted to load in all F's, okay, which is a signed number, what is all F's? What does that represent? Signed, not unsigned. -1. Right? Remember? Yeah. Why? Okay.
I know the -1.
So if you've got a number in binary, how do you negate it? You flip all the bits and then you add 1. Right? So if all of your bits are 1 and you flip everything, what do you get? All zeros. If you then add 1 to that, you get, well, 1. Okay? So if flipping the bits and adding 1 is equivalent to negating the number, and you do that to a bit pattern and you get the result of the value 1, then what did that mean that you started with? -1. Okay? Just 2's complement, right? Did you guys learn 2's complement with Will Coxon? So you did? Okay. Arthur, did you learn 2's complement? Okay, we better chat sometime. It's not rocket science, but yeah. Okay. Anyway, we'll deal with that later. Yes, so if you wanted to load in all F's, then using the move K instruction, it would take 4 of them. A move Z followed by 3 move Ks. Okay, which is 4 instruction. That's a lot, but you can do it with just 1 because there's also The move in instruction. The move in instruction does the same as move Z, but after you do it, it negates everything, okay? And when I say negate, really I mean logical not, okay? So let's say that I did move in register 0 FFFF. What that would load is, if I did move Z, what would it do? It would put the FFFF in the far right spots and zeros everywhere else. Yes? Okay, what about if I logically not all of those bits? What does F turn into if you not it? 0. Okay, and what does 0 turn into if you not it? F. Okay, so what about, so to Cole's question, if I did move in, if I did the following operation, move in W0 or X0, whatever, 0, what would get loaded into that register? Either W or X, either way. Well, what would move Z with 0 load in? All zeros, okay? So if I load in all zeros and then I hit the not button, then what is everything going to turn into? In hex, all Fs, okay? So actually, I could do it with a single instruction instead of 4, like we thought a minute ago. Yeah? That's kind of clever. You don't seem convinced, Mr. Powell. I don't know. Are you going to try and find me a gentleman coin because of this, or? I don't know. There's a few people missing today. Maybe they should be fined a gentleman coin. Oh, you do? Ah. So, for example, where's Ajay? Huh? What's? Oh, so we now have a miscount. Ooh. Okay. Yeah. All right. So there we go. So yeah. So the instruction. Oh, we already talked about all of that. Okay, negation. Okay, here's the second approach that we could actually use to get the number -1 or all F's into a register, which is just load in 1 and subtract it from 0. Right, that would certainly do the job. Okay, however, how many operations is that? 2, whereas with that other one, we could do it in 1. Okay, so anyway, yeah, so that certainly would work too. All right, so the next thing I want to talk about, well, first off, let me pause. Any questions, preguntas, and or fragans? No, that was a lot. Huh? You need some coffee first to decompose this? It'll sink in. I'll give you guys, actually, maybe we'll make homework 6 will involve the 3,000 page PDF. Or 7. Yeah. No problem. I'm not going to run out of numbers anytime soon, right? And well, and I forgot to mention that I count in hex for these, so there will be a homework 0F.
You should stop at number 8 just, to the accreditation and the 8 thing to follow that.
But it would actually be 9 because we started with 0.
So we still 7. So 7 is the
can only have 7 assignments? Okay. Right. Kids these days. Okay, let's talk about flags. Okay. Yeah, now, like, when I say this, I don't mean like Sheldon and Amy's fun with flags on Big Bang Theory. No, I don't mean those kind of flags. Yeah, sorry. Nope. No, we're talking about processor status flags. Okay. Yes. Okay. So ARM processors, like basically every processor that's existed for, since we've been making these things, um, has a special register called a flags register or processor status register or something, okay, that contains a bunch of bits, and each of these bits means something important in terms of what the processor did or what state it's in or something, okay? 4 of these are the N, Z, C, and V flags for negative, zero, carry, and overflow. Okay, and the result of doing certain operations can set these flags. You can also clear them. Um, and you can use the flags as a basis to make a binary decision. Okay, so what we're really about to get into with this is how do you do conditional expressions? It all comes down to basically the flags. Okay, so let's suppose that I added 2 numbers and the result was 0. What would the 0 flag get set to? It would get set to a 1. The result was 0. Okay. Maybe doing an addition doesn't change any of the flags. Okay. Maybe it causes a carry. Maybe it causes an overflow. Okay. So depends on the operation, and it depends on what exactly you're doing. And now there's one distinction I want to make here, which is the word flag setting. Okay. Not all instructions actually set the flag values. Okay. Some do and some don't. And let's look at the distinction here. Okay. So, for example, there are 2 flavors of add. Okay. We used the regular add instruction before. What does it do? It just adds 2 numbers. The add S instruction does the same thing, except it will also set a flag if needed. Okay, so the S at the end, for the most part, indicates that this flavor of instruction is a flag setting variety, and if the result of the sum, like you add 2 registers, and let's say you get 0, then the 0 flag would get set. Let's say that you add 2 registers and you get a negative value, meaning that the far left bit is a 1, then the negative flag would get set, okay? So it's going to update the the appropriate flags based on what kind of result you get. Okay. All right. Is that okay? So if you use the regular add instruction and there's a 0 result or an overflow or something, it is not going to change the flags. Okay. That would not be a flag setting variety. If you throw the S on, then it is a flag setting variety. Okay. Is that okay? Yeah. Okay. So for example, one of the things you could use this for would be, well, let's say you wanted to do 256-bit arithmetic, but your processor's only got 64-bit versus arithmetic. Well, if you have a carry, then you could load that into the next 64 bits, right? So you could build kind of compound arithmetic out of this. But there's also a lot of other things you can do. We'll get to that in just a second. Now, in addition to flag setting instructions, there's also flag reading instructions. Okay, and And you can also therefore have both flag setting and reading. Okay, so add with carry takes into account whatever the carry bit is. Okay, so if I add two registers together, and I care what the carry from the previous addition is, then I would use ADC, and what that would do is say take the two registers and add them, but then the carry bit is either a 1 or a 0, and add that on also. Okay, so let's say, for example, that register R had 2, register S had 3, and the carry bit was a 1. What would the result of ADC be? One register has 2, the other register has 3, and the carry bit's a 1. What would the sum be? 6. Okay, if the carry bit were 0, what would the sum be? 5. Okay, so it just depends on what that bit is. And that may make a difference depending on what you're trying to program. Okay, now the ADCS one would also then set flags after it's finished with the computation. Okay, so you can set but not care about, you can care about but not set, you can care about and set, or you can neither care about nor set, right? So all 4 things are possible. Okay. And yeah, I don't know, maybe this would be good for an even further assignment about addition with 128-bit numbers. Yeah, yeah, this sounds like a great idea. Okay. Well, see, I think what Cole has probably learned is don't ask questions, because then McKinney spends another lecture on something that going way too deep into the answer to that question than he ever could have desired.
It's like a kid at the end of class in high school. It's like, oh, are you taking the homework, or are we turning in the homework today?
And the professor's like, oh yeah, the homework. Thanks for reminding me, Cole.
All the kids just hate him.
Yes. Yes. Okay. Well, so the bathroom's just down at the end of the hall there. You guys can all drag Cole for a swirly. Okay. Or stuff him into a locker or something.
Yeah, it's too early for that.
Yeah.
I'll do anything for gentlemen coins.
Okay. So, now, what this really is important for, okay, those of you who took 101 with me, you remember the Brookshire stuff? We had the jump instruction. Yeah? Okay. Those of you who didn't, whatever. Okay. So let me scroll down. We get, let me actually go down to here. Okay. So there's an instruction called compare. Okay. And a comparison, you need to specify 2 registers. Okay. Now, what it really does is it subtracts one from the other. Okay. But we don't need to worry about that right this instant. But by subtracting them, what would happen if the 2 registers were equal to each other in value? And then you subtract one from the other. What would the result of that subtraction be? Hopefully 0. Okay. And if you then set the flag register based on that, what would the 0 flag be? 1. Okay. So if you do this comparison and the 0 flag turns into a 1, what does that tell you about the 2 registers you started with? Their values were equal. Okay. And so you can use that as a basis for a decision. Okay, so think about like in C or Python or whatever, right? Anytime you wrote if and then a condition, then do something, right? And maybe you had an else, right? You were trying to check whether or not something was true or false, okay? But ultimately, what does everything come down to on the machine? Some sort of arithmetic, okay? So if we want to say, all right, if the values in these 2 registers are the same, go over here, then you would first do a comparison and then you would do a branch, and we'll talk about the branches here for the rest of the today. Okay. Okay. So let me go back up and let's talk about branching. Okay. So how many of you guys ever programmed in BASIC, like on your calculators, for example? Like, did none of you program like quadratic formula programs on your calculators in algebra to cheat on your homework? Huh? Well, you know, I wrote programs to check myself. Yeah. Yes. Of course you cheated. Oh yeah. Yeah. Okay, so seriously, nobody has programmed in BASIC before? None of you at all? You can. Okay, so forget it. None of you have seen BASIC, so it won't make any sense to make this analogy. But okay, if you are, well, okay, let's go back to a listing file. Okay. And in fact, let's go to a listing file from one of our examples. Let's do, oh no, I didn't make a listing file there. Now, let me just open this one. That's good enough for right this instant. Okay, so where I've put main, right there, we had to have a routine called main because we were using GCC. Okay, just had to be there. Okay, main is called a label. Okay, and I could have as many labels as I want. Okay, so for example, when we did like the Fibonacci thing, right, you made two functions, a recursive version and an iterative version. Okay, and you called those something, right? Well, each of those things in the assembly would actually end up being a label. Okay, and if I want to do a loop or a jump command, okay, basically what I'm doing is I'm going back to a different line of the program, okay? And I'm doing so, and that's called branching, okay? Now, you can branch to a label, which really is branching to a memory address. You're saying, okay, take the program counter, set its value to this memory address, and then start executing whatever you find there, okay? Now, that branching, okay, can be conditional or unconditional, okay? Unconditional would mean that it gets executed no matter what, right? You always go to it. Conditional would mean that you make a decision as to whether or not you do this jump, okay? Now, what basis do we have for determining whether or not we need to jump? Well, okay, in a high level language, an if statement, okay, but in terms of like the actual processor, what do we have? Flag registers, right? We use the flags to tell us whether or not we're going to make a jump, okay? And this is unfortunately going to have to wait until after break, but yeah, okay. So, all right, so let's simmer down now, simmer down. Okay, so we talked a lot about instruction encoding, okay, and stuff like that. I'll come up with another couple of diabolical assignments, right? Just to keep Farden entertained, right? And we'll talk more about the like jumps and stuff when we get back. Okay. All right. See you guys later.